So, for the longest time, if you wanted to look way back, I mean, way back to the universe's earliest moments.
The cosmic dawn, yeah.
Right, when the first stars were just igniting, the standard thinking was, well, you absolutely needed a space telescope.
Like Hubble or now James Webb.
Exactly. Because Earth's atmosphere, it just seemed like too big a hurdle.
It really did. It blurs things, absorbs light, trying to catch that incredibly faint ancient signal through all that mess. People thought, well, basically impossible from the ground.
But here's the thing, and this is what we're diving into today. There's this amazing challenge to that idea coming from, of all places, the Atacama Desert in Chile.
High and dry. Good spot.
So our sources show how telescopes down there are doing something people thought couldn't be done. Peering into that early time, specifically getting light from the reionization era.
Yeah, our mission today is sort of unpack how they're managing that from birth and, why it's such a big deal for understanding how everything got started.
Okay, let's back up just a touch. The cosmic dawn, the reionization epoch. What exactly are we talking about?
Right. So after the Big Bang, things cooled down. Atoms formed mostly neutral hydrogen. The universe was dark. The Dark Ages.
Okay.
Then, maybe a few 100 million years later, gravity starts doing its thing, pulling stuff together. Boom, first stars, first galaxies. That's the cosmic dawn.
Got it. And the light from those stars.
Exactly. Really intense ultraviolet light. It started knocking electrons off those neutral hydrogen atoms again, reionizing the whole universe.
So it was dark, then lit up, then the lights really came on everywhere again.
Pretty much. And that whole reionization process, it took maybe 1 billion years. Detecting light from that period is like seeing the universe switch back on.
And doing that from Earth seemed impossible.
Now, sources mention techniques like adaptive optics.
Yeah, that helps with the atmospheric blur for taking pictures, essentially. Sharper images.
And interferometry.
Yeah.
Combining telescopes. Also great for imaging, getting really fine detail on distant galaxies. But this breakthrough, it's different. It's about detecting a specific kind of light.
Which is?
It's polarized light from the cosmic microwave background, the Big Bang's afterglow that actually bounced off those electrons during reionization.
Right. Okay, wait. Polarized CMB light.
Yeah.
That sounds even harder to catch. Where does this class telescope fit in?
Class S. That's the key here. Cosmology, Large Angular Scale Surveyor. It's up there in the Atacama.
Right.
And a team, including Yunyang Li and Tobias Marriage, they just published this landmark paper. They've actually done it. The first ground-based detection of that specific polarized signal from the reionization era.
Wow. Okay, why is that specific signal, the polarized bit, so ridiculously hard to see from down here?
Well, two massive problems. First, the signal itself it's incredibly faint, like about 1 million times weaker than the CMB's total brightness. It's barely there.
1 million times fainter.
Yeah. And second, Earth is just screaming with radio noise in the exact same frequencies. Satellites, radar, even Wi-Fi and microwaves. It's like trying to hear a pin drop during a rock concert.
Okay, so how on earth does class filter out that concert to hear the pin drop?
Cutting edge stuff. They use these incredibly sensitive detectors, cooled down to near absolute zero.
Why so cold?
To stop the detectors themselves from adding noise, basically, minimizing their own heat signal. And really clever shielding, designed specifically to block radio waves coming from Earth, let the cosmic signals through.
But even with all that, how do you know for sure? How do you know it's the signal and not just some leftover Earth noise you missed?
Crucial step, validation. They didn't just look at their own data. They compared it meticulously with data from space missions, NASA's WMP, ESA's Planck.
The ones that map the whole CMB.
Exactly. By comparing the patterns seen from space and from the ground, they could filter out, anything local and be really confident the polarization came from those ancient photons hitting that reionized gas. Tobias Marriage put it nicely. He said this proves what cutting-edge technology can achieve from the ground.
And Clad's been working on this for a while, right? Mapping polarized light?
Yeah, they did a previous survey mapping about 75% of the sky. This new work is it's a huge leap in precision, really zeroing in.
And it's more than just a technical achievement. It tells us stuff.
Oh, absolutely. Big implications for cosmology. As Charles Bennett, another expert, points out, getting better data on reionization helps refine our cosmic laboratory, meaning
Right.
it helps pin down the timeline. When did reionization really happen? How fast? That puts tighter limits on how galaxies and clusters formed.
I see.
And because that process is affected by things like neutrino mass or dark energy, well, better reionization data helps us measure those fundamental things better too, like the mass of neutrinos,
Yeah.
testing dark energy theories. It all
Yeah.
connects.
So the really big picture here is, wow, ground-based telescopes in the right place with the right tech are genuinely opening a window onto the universe's first billion years, seeing light we thought only space telescopes could.
That's the takeaway. And they're not stopping. Class wants to push sensitivity even further. They're also looking for something even more subtle.
Which is?
These specific B-mode polarization patterns, tiny twists in the CMB polarization that might, just might, be faint echoes of gravitational waves from cosmic inflation right after the Big Bang. The ultimate prize, really.
Incredible. It really makes you think then, if ground telescopes in places like Atacama can achieve this level of sensitivity now, looking at the universe's first light, well, what other impossible observations might become possible from right here on Earth in the coming years? Something for you to ponder.